Alright, now it's time to talk about nuclear chemistry. So nuclear, radiation, words like that you guys are familiar with. You've heard, if anyone's ever seen any form of science fiction movie, more than likely you've heard those terms just thrown around like they're candy. But we're going to talk now about exactly what it is. This is a great unit because a lot of the stuff that we see on here has real-life applications. This is something we're all familiar with, but we don't really understand. And that's true for most of the American population, most of the world population. We talk about nuclear, we talk about radiation, but do you really know what that is and what we mean when we talk about radiation poisoning and cancer and nuclear power? Well, after this unit, you guys are going to have a little bit better understanding of what that means. You'll actually be able to argue with some of the things you see on the movies or even in the news. So once again, nuclear chemistry zooms in on the single atom, just like we did for the last unit. So we know that inside the center of an atom is that nucleus, and around on the outside is that electron cloud. So we've talked a lot about this area out here. That's the electron cloud, the electrons, the 1s2, 2s2, different orbitals, different sublevels, all of that. But as you might have guessed, the nuclear chemistry doesn't deal with the electron cloud. It actually deals with the nucleus, hence the name nuclear. So we're now going to zoom in and take a look at just the nucleus. So for a bit, we're not going to really be talking about electrons. Keep in mind they are there, they do play a role, but their area is more with bonding and chemical reactions. They don't really deal much with the nuclear chemistry. So we're going to zoom in and take a look at just the nucleus, which is just protons and neutrons. Let's run a refresher on the nuclear notation. So nuclear notation, we've got our atomic symbol, then up here we had the atomic mass and the atomic number. So I'm going to throw a new word out there, and that new word is nucleons. So nucleons are things that are found inside of the nucleus of an atom. And so then the nucleons would be the protons and the neutrons. So then, of course, electrons would not be nucleons because they're not found inside the nucleus. And so what this also means then is the number right up here, the top one, 238 in the case of uranium, doesn't just have to be the atomic mass. It can also be the number of nucleons inside of the atom. And so that's what we're going to start considering it for this unit. It's the total number of nucleons for that particular element. So uranium-238 has 238 nucleons. Now this bottom number tells us the number of protons. And so that means if there is 238 nucleons and 92 of those nucleons are protons, then it's very easy to figure out the number of neutrons. The number of neutrons would just be the total number of nucleons, 238, minus the number of protons, which would tell us the inside of this particular element there is 146 neutrons. So let's take a look at a nucleus real quick. Remember, it's got protons and neutrons. Protons are positively charged, fellas. Neutrons are neutrally charged. They're both roughly the same size, same mass, and they're packed together very, very tightly inside of the nucleus. Take a look at the nucleus. I mean, a close look at the nucleus. There should be something there that stands out to you as being a little bit strange. We've got this densely packed region. What's wrong with this? Yeah, if you know anything about charges, you should be able to recognize then that we've got two positives really close to each other, in fact, crammed in close to each other. So what is it that keeps them from just flying apart? When we talk about electrons, we talk about how they want to be as far apart as possible. But when it comes to the nucleus, suddenly we have positives crammed in right next to each other. Well, what we have here holding it together is what's called the nuclear force. I won't go into much detail about it, but what happens is when we bring like charges close together, there's kind of a sweet spot where they actually somewhat attract each other, somewhat repel each other. And so nuclear force is then what holds those protons together. Also, the neutrons, which are neutral, act as kind of a buffer. If we had nothing but protons in the nucleus, it couldn't exist. Okay, they would repel each other, they would fly apart. But when we throw these neutrally charged particles in there, they kind of act as a mediator to hold things together. It's like if you have someone you don't really like, but you have a friend in common. When you're with that friend who you both like, you kind of get along all right. So these protons, even though they repel each other, well, they got their neutron friends there who are neutral. They kind of keep everything safe. So when they're around, they keep the nucleus together. So then there's two things that are counteracting or acting inside of a nucleus. The first one's the nuclear force, which is holding it together. And then there's also the repulsion force. also known as the electrostatic repulsion force. So electrostatic, that just means charges. Repulsion means they're pushing away. And force, that's just kind of the oomph behind it. So what electrostatic repulsion would be then is like charges repelling each other. So these two protons right there are really pushing against each other, but the nuclear force is holding it together. So inside a nucleus, there's actually a very delicate balance between the nuclear force and the repulsion force. So if the repulsion force gets too great because of too many protons or something, it's going to cause it to fly apart, essentially. It's going to repel each other too much for the nuclear force to hold together. So we would say that an atom is stable only if its nuclear force is greater than its electrostatic repulsion force. As long as this value right here, the nuclear force, is greater than this value right there, the repulsion force, the atom will stay together and everything's happy. But hey, that's not that cool, and that's not what this unit's about. It's actually about if we flip-flop this. So what happens if the electrostatic force becomes stronger than the nuclear force? So if the repulsion is greater than what's holding it together,